underscore L will be used. These are the views I'll be using. And if we open an Oracle hardware guide, then you'll find this all underscore views retract public authorization, so all users can be accessed by anybody. First, I check once I got app user access, I check the users. I will find this one, suspect, app ngr. Obviously, the name is not all something. Then I use an all underscore to check his authorization, his privileges. In real life, it would be a bit longer, but here I found a stored procedure that returns the authorizations, returns the privileges once I check it. I check the stored procedure, and if you see something like this in a code, if you see this in a string concatenation, then this is a code injection error, which allows me to change the select statement contents, and this allows me to access data that can be considered sensitive, because in this users table, to which I have no access to, basically, I have the salaries of these people. So the red part shows you how I could access not only the users, but also their salaries. Rootkits. Alex Combest in 2006. Okay, we are talking about database rootkits, not operating-based system rootkits. So Alex Combest classified these. The first generation was about were used to modify views and stored procedures, which means that okay, so the users view that we saw before was created by select, and we changed the select condition so the hacker user does not show up when somebody is checking who is using the table. The second generation already could, for instance, modify Oracle binaries themselves, so you could rename tables. And the third generation is already able to actually work in Oracle's memory in the SGA, where a lot of things are stored. For instance, you can do byte or bit flipping to give yourself sysdba authorizations. David Litchfield had a presentation that examined this. He demonstrated that he could load a DL in the Oracle process that opened up a share. Another one was more interesting. That it allowed him to use an exploit, a buffer overrun, to inject code into Oracle's memory that replaced system users' password hash to something he knew, so he could actually then log in afterwards as a system user to the database. And I have a personal preference, which is very clever, done by Denis Yurichev, who took out the .o object file from an Oracle library. He wrote an object file himself in C, and then injected this his own object file into the library and relinked Oracle. This is a second generation rootkit, if you like. So this is the neuralgic point. In Oracle database, a lot of passwords are stored so Oracle can communicate with others. So these passwords are needed by Oracle, but obviously these are encrypted. These are the database links that are encrypted. The EM passwords, Metalink is also encrypted, which is a username password to Oracle's website. Here you can set a web proxy password or some database user passwords. And Apex is also encrypted. The remote job scheduler has stores passwords here, for instance. So what I need to stress here for Oracle is that what I'm talking about are post-exploits. In order to get these passwords, you need the highest level of privileges. And the database link password is the worst thing that can be published, but obviously and it hasn't yet. But all Oracle specialists know that this is the most neuralgic point of security here. What I'm going to show you instead of this neuralgic thing is how Enterprise Manager is coded, because this can be changed in 11G. I have highlighted 05 here. Okay, before 11G, you only had to call syscom.decrypt, and you received the underlying password. Since 11 years, it's not so anymore. The key is stored in an operating system file, and the 05 is highlighted here. And this is already a secret I'm divulging to you, because anything in Oracle that is encrypted and an encrypted byte sequence and started with 05 is this specific algorithm. So I take the first 8 bytes except 05. This will be the key. And the remaining part is the encrypted part, and a simple DES is used to get it. So this allows me to get the key. Once I have it, obviously with high authorizations, privileges, I call this procedure this stored procedure with this password, and from that point onward I can call syscom.decrypt, and I get all the passwords. And here's the proxy password that could take me even further. So let's get then to the essence. We are talking about DLL injection. I've done this on Windows and on Linux, although on Linux they wouldn't call it DLL. On Windows I used a very simple technology, but on Linux it's a lot more different, and there are not many examples for it, how you can load a library with ptrace and then change program run afterwards. I'll talk about this a bit more. For the time being, the proof of concept codes are 32 bits, but there's no problem creating a 64-bit one. As Linux is a more interesting example, I found one example at the time I wrote this presentation. That was the SSHF in Frac Magazine number 59. Since then, a lot of things have changed. Also in glibc, I used to be open to load a dynamic library into program memory, but its access has completely changed since SSHF, so this had to be recoded. It also had a more simple part. It logged bar calls, and in order to call the initial PAM function, the only thing it did was to link the library, and it became more simpler to call the PAM library then. What was in this case more difficult in Linux was that on Windows everything is DLL, but on Linux practically everything is contained in the Oracle executable, which is 166 megabytes, so it's a pretty hefty bit. The injector program links to the Oracle process using ptrace, stops its running, starts DL open, which is a standard system call, so it must be there. Then finds the address of isAlpha function, which is also a standard library. This is needed to find an address that is for sure contained in the Oracle executable, and then at the beginning of isAlpha, it writes the shell code shown in the picture. The DL opens address will be written here once I found it dynamically in memory, and this is a flag parameter of the DL open call. It's also a dynamic. I dynamically in the command line I enter the command line access path, the route. The jump enter and call start trick injects into the stack before the 01 this access path. So we have prepared the stack for the DL open call. We call DL open, and we said, and then we stop the program run with a debugger breakpoint. Once the program run stopped here, I find in memory the addresses of the functions I want to redirect, and I also find in the loaded library the addresses of the functions I want to redirect to. On the top picture, you see a redirected call. This is a normal function start, but I use ptrace to get the bottom part. I only inject 2 instructions, but ptrace, for certain reasons, needs some more. This is the address I want to redirect to. If afterwards I call ret, when this is at the top of the stack, then this is loaded into EIP, and this is the point where program running will continue. So once I did what I wanted to do with the parameters, here's my function using inline assembly instructions shown in the debugger. I put the stack in order as if I just called the initial function, and then the part that I rewrote, I have it run at this point, and then I have a jump instruction to jump to the unmodified part. And another trick, the last data I push on the stack is a memory address that will jump into the NOP slide of my function. This allows me to handle the return values instead of the original function, and I can even bring the stack in order before returning to the caller. What are the other differences between Windows and Linux? One is that Windows is multi-threaded, while Oracle the Oracle process on Windows is multi-threaded, so one process, the only thing you need is to attack one process, while on Linux, Oracle is multi-process, so you have to attack multiple processes if you want to redirect everything. But on Windows, due to the applied redirection technique, it is not sure that I can redirect all calls. For instance, if a DLL calls a function it contains itself, one that I have already redirected in the Oracle process, then this one will not redirect. But in Linux, it will happen every time. The redirection will work every time. In theory, both problems have solutions. On Linux, this process forks the Oracle call when somebody logs in. So it's enough to use, for instance, the shell script to check new processes. So in principle, it's OK. On Windows, we can implement something similar, like what we did on Linux, for instance, in a next version maybe. So what have I redirected? I concentrated on crypto because this is a very hot topic, and secondly because you can implement crypto in the database itself. There are two Oracle packages that implement this. That allows you to implement cryptography in DBMS code. If you have listened to me last year, you will know that there are a lot of cryptography in the authentication itself. We have talked about the transparent database encryption, and we've seen that seen how many encrypted things are stored in the database. The DBM's obfuscation toolkit was the earlier version, which was replaced by DBM's crypto desk. It supports a lot more algorithms. In Linux, these are called in the Oracle process, and if you look at the bottom, practically all functions in the package will be converted to these three Oracle calls. On Linux, on Windows, sorry, these are in DLLs, specifically in these two DLLs. And before doing the demo, I'll use this function for the demo. This is an encryption function with AS. I give it an input string and a key. From the key, I create an MD5 hash, and this will be the MD5 hash that I will use as a key within the encryption itself. It has its decrypting pair, a decrypting function. And then let's start the demo. First, I inject into Oracle. For this, I need the Oracle process ID. And I managed to actually drop Oracle, so I'll really have to start it. Okay, looking for the Oracle process ID. And let's hope we have not managed to bring the database into a state from which it cannot start. Okay, so the transparent database encryption was introduced with 10G release 2. Unfortunately, the advanced security option, which means that we need to pay up to Oracle a bit more, it could encrypt in 10G on a column basis, which means that when we created a table, we could specify which column should be encrypted. In 11G, the whole thing works on a table space basis, which means that the table space will be the file on the that appears in the file system. And when I create a table, then I can say which table space it should be in. That if it is an encrypted table space, then the table data will be encrypted. The database is up again, so back to the demo. So we'll PS list Oracle. I'll be doing the injection as a system user, as you can see. That was it. And if now we look at the log, then we'll see that there is a lot of debug messages which don't matter, but these are not important yet. Next step will be to enter Oracle, and on purpose by showing you the password, which is pretty hard to break. And now you can see that this is basically this is a TXT file, and you can see that the password has been logged. So once we have done the injection successfully, anyone entering into Oracle, we will log their passwords. So the log will write their passwords. Now, if we send the SQL select that does encryption and decryption at the same time, or obviously consecutively in one batch, what we see is that we call the encryption for a text of BBBB with a key of AAAA, so we should get back 4 Bs. And if we look at the log window, we can see that we have managed the encryption and decryption. So these are the hash functions. Here we see the 4 A's as input, and we see the result, the output. If we, okay, this is the encryption part with the key we generated before. The 4 Bs are shown in hex, and this is the output it was changed to. Then the decryption does the same hash on the 4 A's using the key, decrypts this thing, and we get back our 4 Bs in hex again. There are a couple of important information about TDA. First of all, everything is based on a master key, which, however, is not stored in the database, but in a stored wallet in a file outside of the database. TDE does not protect data in the file system. Protects the data on the file system, not in the database. So if you make a file level backup or pull out a disk, then it's about the protection of those data and not the protection of the database. Because if the wallet is open and we need to open it to access the data, then Oracle's authorization system will decide whether we can gain access to those data or not. What does it look like when we only have column level encryption in the 10G version? As I said, there is a file in the file system from which Oracle loads the appropriate master key after you provide the appropriate password. If the user wants to access a column that is encrypted, then Oracle will based on the object identifier, check the table key stored in a separate table in the ENC dollar. This key is encrypted, so it has to be first decrypted with the master key, and once this is done, then we can decrypt the encrypted column. Anybody counted the number of decryption I used? Number of decryption words I used? The same happens in the case of table spaces. In this case, the column is not encrypted. The entire table is encrypted. So the master key comes from the wallet. Table space key comes from the table space file. I'll show you in a minute where. And when you select into such a table and you're not yet in the cache, then Oracle will read at block level from these files. It will read one block at a time, and that block obviously is encrypted. Then Oracle decrypts using the table space key, decrypts the block, and the clean text data can then go to the user. After the presentation, you'll probably ask whether this slide or the previous one had more occurrences of encrypt, decrypt. Okay. Oracle handles files at block level. The tablespace key is the second block of the tablespace file plus OX0100. And this is the byte that tells you the key length. Then it follows by a 16-byte key, which means it is 128 bits long. There is also an IV that you will need for a good cryptographic system. Each block has a separate IV, its own IV, to be found at the beginning of the block. In this way, so this is information I gained by experience. Before starting the demo, I'd like to ask my colleague Tóth his effort to implement an Oracle wallet dumper in his spare time. David Richfield must also be mentioned, who created the Cat5 toolset, in which contains an Aura block device, which means that if I have which I can use to extract data. I had to modify it a bit because my examples didn't work with it unchanged. And I'd like to express my thanks to J. Dudes, author, who allowed me to view his commercial product for free. This device, this tool can be used on a collapsed, on a broken database to still get out the data from it. I used it to check whether my tablespace files I created myself correspond to the expectations of the Oracle database. As I said, everything depends on a master key, so I have to open the wallet. With this command. And if you look at the log, you see a lot of encryption, decryption happening. But what is important is afterwards, but you can't see it yet. But a lot of W's should be here. So this is the online demo. I didn't really manage it right, but I can actually get the wallet password, and I'll make another try. And now it succeeded. This is the wallet password. And before exiting Oracle and continuing in offline mode, let's look at the contents of the table that is in an encrypted table space. Here you can see this is the table contents. If we check these contents in the injected part, you can see that these are the data in hexadecimal. The lots of Q's and B's can be seen here. So any TDE encryption, decryption can also be logged. In order to make this work also in forensic cases, or in case you only have the key, we first dump the master key from the wallet using my colleague's program. We have the key, but we could also use brute force to get it. And despite the name, this is the key we're interested in starting here. This is the master key, and this is a key identifier. Once we have the master key, then I'll use my own small C program that takes the master key and the tablespace, an encrypted tablespace file as a parameter, and it will output the tablespace key for me, decrypting it practically for me. And we can also check if this really works. If we check the description shown here, it is the same tablespace key, so we even log this attack. If we look into this tablespace file with a string command, we'll find I specified for it to output character chains of more than 10 characters. It didn't write anything sensible at the moment, but if I use my other own program that takes tablespace key as an input and the encrypted tablespace file and the place to save it to, then it will do that. And if we check the decrypted file, then we see the data. Lots of Q and B letters. So this was the encrypted tablespace. Before demoing the column decryption, let's check what it looks like in the tablespace file. This is the row stored. This does the row length. This one does the column size. This is the encrypted column. It has an SHA-1 hash for integrity. Both can be turned off for performance reasons. If we now attack this, I said that the table keys themselves are stored in the ENC dollar table. This is where I'll use the somewhat modified Aura block tool. I take out object 400 from the system table space, the contents of it, and I'll tell it what the different columns are, and I redirect output to this file. This will take some time. So while it's running, let's dump an object one of whose columns is encrypted. I'll also use the Aura block tool here. And if we check the contents of this file, I used Aura block to dump from the table space this object ID, and the object's contents are shown here. These are the lots of Qs and in hexadecimal, and this is the encrypted part. We must be patient while this finishes running. Successful. And what you saw, the program that you saw has another function. From this output, which we have just generated from the ENC dollar table, you see that I called the same program, but the T parameter is now 1. This is a type, and I used the output of the previous dump, and you see that it even also parses the table contents. and these are already decrypted table keys. This is the object I'm going to investigate. This is the key identifier. This tells me the encryption algorithm, whether there is or there isn't a hash. And obviously, there is a separate program for this purpose as well, for the purpose of decrypting the columns. I specify the successfully acquired column key, the object contents, and the place to dump it to. And this is, if I now check the result file, I see lots of B's and a lot of C's. I send it to that table. So as you could see, we can walk through the TDA, which may be very useful in forensic cases. Now, some words about remote job scheduling, which is a bit different, but not that different from what we have heard about. It was introduced in 11G. Oracle itself has a job scheduling engine, and in order for it to be able to run commands on remote operating systems without having to install a complete database at the remote side, remote job scheduling was introduced. Obviously, it does need an agent. How does it work? There is a Java agent, SH agent, that accepts the connection from the network. SCH agent calls the GSSU executable in the Oracle bin directory, and the result is sent back to the database through XDB instead of returning them through the same path where the queries came in. What is the security of this solution? It's not a bad design, actually. The network connection to which job requests come in is encrypted with using SSL. In order to run a job, you will need a username and password on the computer where the agent is running. In order to handle this in the database, they have created a credential object to which access rights can be attached. And for all this to work, the agent has to be registered into the database using a registration password. So it's a pretty well-designed stuff. But what is the problem is that in release 1, the data returned as the job results are not encrypted. As of release 2, you can encrypt the return data as well. This is what a registration request looks like. This is a plain HTTP request. That's an HTTP server receiving it. It sends the certificate. This is the SSL certificate of the SH agent for the database to check if it is connecting to the right agent. The registration password is sent hashed, and the shared key is returned, sent encrypted. This is the shared key that in release 2 will be used to encrypt the results, the query output. Now, what happens in the database after we register? The shared key is stored in this table. We need high privileges to access it, so they are used in this table. This here is not encrypted. In this key is stored something else that is important, but I will not talk about it. And this is a credential. This is where I can create a credential. This is the way to create a credential. It has an object identifier, a username, and a password. And once this has been created, it will be stored in this table. It looks like in a form that looks like base 64. And this is the block that we use to run the command on the agent's operating system. Here I pass the credentials and the target. Now, the encryption of the credential password also is DES-based, and the first 8 bytes must be extracted. We skip a slide again. But this is not the only way to do it. I can also log it. This is the shared key. I redirected this function as well, so I can grab the shared key used for authentication, and these decryptions that are performed at password level can be done with this function, and these are the passes. Security 2. What else can I do? I can disable put file and get file. I can disable job execution as a whole, but then why did I install the agent, obviously? And there are two important parameters that allows me to restrict users. I can specify who can run commands through the agent. Those of you who sit here will probably know immediately which of these two parameters should be used. I have also mentioned that as of this new version, there is an encryption. I said that in mixed environments we can guess where this will be set, what this will be set to, but it's a positive thing that if I install an agent like this, then this value will be true. So once you break into a database, you can get out or log the passwords. You can send requests to the agent. The first line of the request is an HTTP request. It's not really an HTTP server. The Oracle agent uses the first 3 bytes only. Anything after the get will be ignored on that line. What it will check for is the username and the password and what I'd like to run. So we can escalate privileges on the agent, and we can also brute force another account. And 2 other comments. Here actually I link to the agent using SSL. Only the first 3 characters are checked because the rest are garbage. And I can query the agent version, which could be useful for the attacker. If shared keys use is set, then this is what is returned, which at least allows us to identify to find out the fact that such an agent is running on there. This was only a place, so to say, but on a Linux. But if you have a working super SU, then be careful who can run the JSSU binary. If you install an agent, there is another contender because we can run commands with a username, password, number of parameters, and a command. So we should then protect this as well. This is why I'm telling you that you should handle not only sudo and su, but also GSSU very carefully. Communication goes through 2 threads, so this is a multi-threaded brute forcer. One thread sends the password, and the other thread checks the outcome. Since communication is encrypted here, even if that parameter is set false and we are talking about release 2, communication is encrypted, so I don't see what is happening, and I don't know based on the returned string whether the password was bad or not. But since this is a plain HTTP and it's a content length here specified, so based on the content length, I can know whether I have found the password or not. Okay, but what if this value is set to true? Then I can log the shared key that I can then feed to the brute forcer. If I want to brute force, if I want to brute force another user through another operating system, then I can do it successfully once again. Questions? No questions? No, we won't have time for that. In summary, never forget that it's not the operating system or the database that is important. What is important is the data. We can easily log in Oracle all crypto functions. This is not a bug. This is a post-exploitation technique. I showed how TDA functions and how data encrypted there can be decrypted, and we analyzed the security of the remote job scheduling feature at last year's activity, László called my attention to it. He told me to check it. I did.